Hi, everybody. This lesson relates back to 61, so I've called it 61B. I just want to give you a chance to actually collect some data and see a distribution result for yourself. And so I just want you to get a die or dice or whatever from a game set or something at your house. Hopefully you can have that. If otherwise, just look for like an online simulator, preferably separately, maybe from the one I'm going to show in a second here. But anyways, so you're going to roll a dice 50 times or so. It doesn't really matter how many times, but a bunch of times, like 50 or more kind of thing. And then just tally up how many times you get each one, right? So tallies, of course, look like, might look like something like this to start it with. And then eventually you get to the point where you get 4 and you do that. So you can count groups of 5 and so on, right? So your chart might look, like this kind of thing eventually and so on, right? Frequency is just the total number. So this would be 5 of those and 3 of those, and 2 of those, and so on, if that was your results. When you're doing your bar graph of it, you want to look at the number of spaces we have. And then, so let's talk about dividing up into the groups here. I think there's 20 spaces, and then we have 6 groups, right? So spaces divided by groups. And so this ends up being like 3. What does that end up being? 20 divided by 6. Only ends up being 3.333. And so if we round up, we need each group to be about 3.3 or so. So if we round down, we'll have room. So if we do in groups of 3, we'd have a group there, group there, group there, group there, group there, group there, and so on, right? So we have 1, 2, 3, 4, 5, 6 groups. And so you could have your bars be in the middle of each of those groups, right? So this could be a bar, and this could be a bar, and so on, right, along the way. So something like that. So just encouraging to think a little bit about how you choose your group sizing and whatnot. So this ended up being 3. What was it again? 20 divided by 6. I think it was like 3.3, right? Yeah, so 3.333. But we need to round down in order to have room in this case, which is different than what I'm going to say in a second for the other one. Your results overall for the table here would be, you take your number of spaces. Again, I think it's 20, and you sorry, not the number of spaces, but you take the total you need to get to. So if your largest number was 16 or something like this, whatever, add this up, 5 and whatever, and then you have the one more. So if we had 16 and divided into 20 spaces, you can figure out what each space would need to be to count up to the top, right? I think I've shown you this before, but divided by 20, so each would be 0.8. So we basically count by ones in that case, and we get close to the top of the chart, right? So the 16 would be up here somewhere. Okay, so this number gave us like 0.8, and so if we round up, to 1 for each space, and then rounding up a little bit gets you, make sure you get to the value by the end of the graph. Anyways, so do a graph like that. This is just the number of results for the individual sides. And then the second version of it is to tally up the number of times the sums add to 2, 3, 4, 5, all the way up to 12. Okay. Yeah. So same idea. Choose your bin width, they call these things, right? Your bin width, particularly for histograms, but kind of makes sense in terms of bar graphs as well. And because we have separate categories here of results, we just have spaces. We have a true bar graph rather than a histogram. So just do a bunch of values. And now in class, when I do this, we end up combining all of the values, and we get a value that we can trust even more because we have so many results averaged together. This is the result we had in the class for the just straight dice experiment. So it's fairly uniform, as it should be, because there's equal chance at each side. And this is the result we got for the sums. And it's close to a Bell distribution, a normal distribution. For some reason, several groups had like one student didn't roll a single 6 the whole time. So there was just by chance some missing sixes there, which should have been really the highest result, and it would have been even better bell or distribution or normal curve. So because you don't have the opportunity to just share all the numbers in a class, I want you to have a chance to see the numbers as they go. So I'm going to run through just the idea of this, and you can do this as well yourself. So you could use this simulator, I suppose, but I want you to have a chance to collect the data one by one like normal. And then the nice thing about this digital version here is that we can see the pattern building one by one. So I want you to set the simulator to dice equals 1 down in the bottom right corner. And then we'll roll dice one by one and watch the distribution form gradually. Just like in your rolling a dice, you might have a particular result come up more often than others. One of my students had 14 ones, and the rest of them were like 5 and 6 and 7 or something. For the rest of them, it was just by chance the 1 came up often. And so if you start rolling a bunch or hit the button that rolls 10 at a time or 100 at a time or even 10,000 at a time, you'll watch the numbers sort of even out. Right? So because the chance is the same for each one, right? So this applet doesn't like the smart board apparently. Switch to the mouse here and reset things. Switch to 1 dice. And so, you literally just roll and you got a 5, and then you got a 5 again by chance, and then you got a 6, and then you got a 3, and so on. You just watch this thing building. And so at first you might think, oh, geez, the 6 has a higher chance. But of course it's not true. And you keep going, keep going, keep going. And, even still right now, the 6 is a little higher than it should be, but it went up again on us, right? So again, that 6 is seeming pretty common, but let's roll 10 at a time, 10 at a time, 10 at a time, 10 at a time, and eventually things start to average out. Now the 1's the highest one. Or if we go 100 at a time, or even 10,000 at a time, things really start to even out. So when you start clicking multiple 10,000 at a time, you see things even out the way you'd expect it to be, right? Equal chance of each side of the die being the result. And if we go to the 2 dice situation, right, start rolling, and so roll, and we got a sum of 11, a sum of 8, a sum of 10, and so on and so on and so on. And so you keep going, keep going, keep going. And, by chance, you might have had a bunch of, I don't know why 1's on the list here, but anyways, that you could have had a bunch of results of 2, like rolled snake eyes, as they call it, right? 2 1's a bunch of times, but eventually that's probably going to even out. And there's only one way to add up to a 2, but there's a bunch of ways that the dice can add up to 6 and 7. So when you start doing lots of rolls, you start seeing 6 and 7 be the most common. Now 10 is higher than it should be by chance. There's less ways to add up to 10 than 6 and 7. So just by chance in your trial, we had 328 rolls, right? So it's by chance you might not have a great looking bell distribution. That's okay. It's just the results you have, right? But when we start rolling hundreds at a time, you'll see the other ones creep up and the other ones not creep up, proportionately, and it starts to look like a nice bell distribution, especially when you start to do 10,000 at a time and so on. Okay, so that's really quite a nice normal or bell-shaped distribution, as should be expected. But 172,000 or 173,000 almost rolls, certainly you're not going to do that in your activity. Okay, so that's the idea that I want you to be able to have a chance to carry out. And like I said, since we can't combine results from everybody in the class very easily, this simulation gives you that opportunity as well. Okay, so just that first page submitting, and if you make your graphs and submit those and so on, that'd be it. All right, so that is all for now. Till the next lesson. See you later.